Hello and welcome to my video, lesson 7.2, nuclear notation. So basically there's a couple definitions that we have to know before we can even get going into this, and we need to know about nuclear notation before we can even write any of the decay equations. So this is an important step along the way, but here are the definitions. Nuclear radiation occurs when there's an actual change in the nucleus, and so it cannot be nuclear radiation. It could be other type of radiation, but if it's nuclear radiation, it would be a change in the nucleus. Other types of radiation are not super dangerous. I mean, if you're microwaving yourself, it's not a good thing, but it's non-ionizing, so it's not as damaging. It's damaging for other reasons, potentially, if you're microwaving your arm, but it's not ionizing, so it's not likely to cause cancer, basically. Transmutation is when we change the element type by changing the number of protons in a nucleus. The atomic number is the number of protons in the nucleus of a given element type. Protons and neutrons are both nucleons and they weigh the same, but protons have a positive elementary charge while neutrons are neutral. Isotopes are when we have two of the same element, but because the number of neutrons present, they are different weights, basically. Okay, so there's the same element, like carbon-14 versus carbon-12. They're both carbon, but one has an atomic mass of 14, one has an atomic mass of 12. An atomic mass, speaking of, is the total mass of the atoms, so basically the number of protons plus the number of neutrons. And we'll talk more specifically about, there's a little bit more detail to that, but we'll talk about that more in the mass defect topic. So nuclear notation is in the form of this, where X is the element symbol. So if it was like carbon, carbon has 6 protons, so it goes at the bottom, and the number of the normal carbon is carbon-12, so it has 6 neutrons and 6 protons. So this is the neutrons plus protons together gives us 12. So it's the atomic mass up there. So let's go ahead and write some of these example questions. I recommend you pause the video here, try it yourself, and see if you get the same answer as me. So example 1, it says write the isotope of uranium-235 in nuclear notation. So uranium is U-235. And then you just have to look up a periodic table, which is in your formula sheet, and you get the number of 92. So this is uranium-235 in nuclear notation. All right, pause it here and try example 2. Write the following element in isotope notation and describe the number of protons, neutrons, and atomic mass of the atom. So this is iodine, and if you're not sure about the symbol, that's fine. Check this 53 on your periodic table. I'll just pull up this Google version of the periodic table so you can see what I'm looking at. Basically, I just go over till where it says 53 over here, and you can see that iodine is 53, and its normal mass is 127, basically, but we have this isotope of it, which is 131. So this is how you write it as in its isotope notation, in its name form. Okay, so the number of protons is given by that 53. The number of neutrons is given by 131 minus 53. And so the number of neutrons is actually 47 plus so 78. So the number of protons, the number of neutrons are given there. Okay, it turns out that the above atom decays into xenon 131. Write this element in nuclear notation. So often what happens is if the proton and the neutrons are wildly different from each other, like if the count is different, then we're often in an unstable form. But another way you can tell is, again, if we look at that iodine here, normally iodine is at 127. So to have it 4 more than normal, 4 more neutrons than normal, is outside of the normal, so it wants to decay. So that's why it does decay. So it changes into xenon this, so it's going to be Xe, and then we have to check the formula sheet, so it's going to be around there, so it's 54. So it's going to be 54 down here, 131 up here. And now to describe the proton count, it's going to be 54 here. And so our neutron count, you're going to see, is 131 minus 54. So our neutron count has actually decreased. And now we have a neutron count of 77, which is probably closer to being happy. When I say happy, closer to being like the normal amount. And look at that, it is 131. And so that's why it wants to decay into that form, is because it's closer to its happy, quote-unquote, happy state. All right, I hope this video helped you better understand nuclear notation and a couple of these definitions. I hope the video helped, and good luck.